Thanks for the introduction. Yeah, I'll be presenting my work on single spike artificial neural networks. And the big motivation for our research has been the fact that time is one of the easiest measurable physical quantity in the world, right? It's really easy to detect when an event happens. A lot of sensors do this, but specifically here you can see something like a dynamic vision sensing camera that automatically gives you a temporal output. And it's also very easy to measure how long something takes, right? This is how LiDAR systems work. They use time of flight sensors, and that gives you a temporal value automatically. And even more classical sensors that operate in the voltage or current domain actually stop in the time domain when we use our analog to digital converters. We convert them to time first and then to binary. And now the fact that we have a lot of temporal information when we're interacting and sensing the world around us gives us the potential to put computation inside this time domain. We can try and cut out that expensive analog or time to digital conversion and use the very energy efficient representation that is a time-based signal to do computation. And another I guess motivation is the fact that the brain clearly uses temporal signals, and it's one of the most energy efficient neural network accelerators out there. So our goal is to put computation in this domain. And one of the most common ways of doing this is through spiking neural networks, which operate on temporally encoded information, and they use activation functions that are biologically plausible, incorporating information across time to generate spikes out at the output. These use fundamentally different algorithms than artificial neural networks, and this has led to some issues when it comes to training them or converting them from artificial neural networks. It's typically quite difficult to get the exact same accuracy as an equivalent artificial neural network, because in order to do that, you need a lot of time or a lot of representation, which starts to remove the advantage that these spiking neural networks have in terms of energy efficiency or performance. So the goal of our research is actually to take the artificial neural network algorithms that we know work really well and implement them in a temporal manner. To do this, we leverage a computing paradigm called race logic or wavefront computing. We broadly call it temporal computation, where the rising edge of a voltage encodes the value. And when you have the rising edge, the value stays high after the event has occurred, which allows us to use kind of standard digital gates. Right? An AND gate in this system actually implements the maximum function because you wait for both inputs to arrive. Similarly, an OR gate implements the min function. And then we can use delay elements to implement addition. These delay elements in a synchronous system could be something like flip-flops, or in an asynchronous system, like the ones we explore in this system, you're just using simple clock buffers to delay your signal. And the final operation that we know how to do quite easily is the inhibit operation. The inhibit operation gives us a conditional. It allows one signal to block another signal from firing. Right? And this inhibit signal, this conditional, actually makes this logic that I'm presenting here functionally complete. But the issue is it can't do full neural networks because we need something like multiplication that is kind of the base for all artificial neural networks. And the reason it can't do that is because multiplication would be taking a delay and repeating that delay a variable amount of time. This requires both fairly complex analog design, and it takes a long time. You have to wait for a large value to be produced, and that large value will slow down your system because you need it before you can continue on to the next computation. So our lab has been playing around with what is formally known as an isomorphic ring, a negative log transform of all our values, which immediately helps solve the issue of waiting for long problems. Values that are large in what we've been calling importance space, when they're transformed through the negative log, actually become very small, which means in time they will arrive first. Right? So we have the most important information to our computation as soon as possible, and then small values that may not impact the computation as much will arrive later and can potentially be ignored. The other nice property that logarithms give us is it transforms all of our basic operations that we need. Multiplication becomes addition. So now we can do all the multiplication using simple delay elements. Addition and subtraction, however, become these complex nonlinear functions called negative log sum exponential and negative log difference exponential, or NLSE and NLDE. Thankfully, these actually have like a pretty intuitive temporal meaning. NLSE is what's known as real soft min, where the function is close to the minimum of two inputs. However, as the inputs get close to one another, the output actually fires earlier, right? So we can use that OR gate, which we can implement a min with, to create a first order approximation of this soft min. However, as the two values get close to one another, our approximation gets pretty bad. And that's where the useful information is contained. So in order to improve this approximation, we found that you can actually shift, you can take a shifted maximum and incorporate it into this minimum function. And you can start to deform our min where information is flowing and you get much closer to that original negative log sum exponential function. And you can continue to add these max terms, and every max term you add, as long as you place it in the right spot, will get you closer to the true function that we're trying to approximate here. And thankfully, NLDE, so subtraction, is very similar to NLSE, except instead of being a soft minimum, it is a soft inhibit. Right? So we can use the same technique we did with the min of maxes with a min of inhibits, except now we're carefully placing where the inhibit is to implement our approximated subtraction. Right? And when you have multiplication and you have accumulation, that is the basis for most artificial neural networks. The only thing that you need from there is an activation function. And the way we handle our activation function is by just using the fact that negative log is not defined for negative values. So we handle all of our positive and negative values separately throughout our network. And then when it comes time to do our activation function, we just use NLDE to subtract the positive value, the negative value from the positive value. And because NLDE is not defined when the value would be negative, it will never produce an output. And never producing an output in time is the same thing as 0 in importance space. So using these three functions, our delay, our NLSE, and our NLDE, we can implement all ReLU-based neural networks. Now, this is really nice, and it actually gives you a very energy-efficient way of doing the computation, but neural networks are huge, and you need a way to fold them across space and time. So you need something that looks like an accelerator, and anytime you do a neural network accelerator, it's going to look like a systolic array. So we take our systolic array and we change our processing element and replace it with our temporal computation. We use a digitally programmable delay element to do our multiplication, and then we use our NLSE functions to do accumulation. And then we have to kind of replicate this hardware, so have one side do the positive side and one side handle the negative side. And then when we're done with the computation, we can perform our NLDE and then store it to memory to make it foldable across time. Now, the problem though is we're using digital memory. And memory is hands down the most expensive operation in neural network inference. So we optimize for our individual operations, our multiply and accumulates are energy efficient, but the thing that consumes 95% of the neural network inference, we actually make worse, because now every time we interact with memory, we need to convert it to time or from time. So really in the system we've set up, we're not getting any energy benefits, because what we get in computation, we lose in these domain conversions. So what we've been doing is we've been using temporal memories. Temporal memories can be implemented in several different ways. There are some analog approaches, like you might see on the right here, or the one that is the most interesting to me is like memoristive ReRAM devices that are programmed using a temporal pulse. And when you have this temporal memory that is programmed using a time value, and then when it's read out, it also gives you a time value, it allows us to reduce all of our domain conversions, and it also simplifies the interface to memory. Because now every time we go to memory, instead of needing to read maybe 8 cells for an 8-bit value, we only need to activate one cell and we get the full value. So this This gives us the potential for very energy efficient memory and very energy efficient computation. But to do this, we've added a lot of potential sources of error. We're working in an inherently noisy domain because we're using asynchronous delays. We're adding more error by using approximations instead of the true functions. And then our memory elements are all potentially noisy. So one of the big challenges that we tackled in this work was creating a very, very tight architecture that tries to reduce error at every single point, right? So in our systolic array, we use broadcasting values every time we read a temporal input to try and maximize our use while it's in the temporal domain. And this broadcasting can introduce a lot of error. So we've taken inspiration from things like clock tree synthesis to really balance the values as they are broadcast to several different spots spatially on a chip to make sure that they all arrive at the processing element as close to one another as possible while limiting any jitter or skew. Then we also use redundancy in our approximations. We do multiple approximations and then kind of take a temporal average to try and smooth out the noise from both the error we're introducing with the approximation and the error that can exist on any of these asynchronous delay lines. Then we also found that because of how we're doing our approximations, the size of each processing element, the number of inputs that each processing element accepts, has a very big impact on the accuracy of the neural network when doing inference. So we analyzed kind of how we can change the size of these processing elements without throwing off the standard data flows that you use in neural network inference. So we're still able to use output stationary or wait stationary while optimizing the tree size for accuracy. And so in order to really evaluate these networks, we did a lot of work on the simulation side where we implemented all of these operations and all of these potential sources of noise into a TensorFlow simulation framework and performed experiments on the MLPerf Tiny neural network benchmark, which is specifically designed for networks that are going to be integrated with sensors. So kind of the application we're looking at. And there's a lot of information on these graphs, but the key thing to note is that the green line at the very top is like a baseline digital artificial neural network accuracy. And the dark blue dots are the networks that we propose. And what we show is we can actually achieve the same accuracy as an artificial neural network for most of these use cases, for all of these use cases, if you're willing to spend the hardware. And so it takes a little bit more energy, a little bit more latency to achieve the same accuracy. But when you do achieve that accuracy, we did a lot of architectural simulation to show that we are still very energy efficient. The purple bar here in our graph showing the energy consumption per inference is a standard spiking neural network implementation, a digital implementation, and that, as you can see, shows the kind of limitations of spiking neural networks. And regardless of whether we use temporal memory or digital memory, we're much better than a spiking neural network approach. But when compared to a digital systolic array, our approach really requires the temporal memory to provide much energy efficiency benefits. But when we use temporal memory, we can get up to a 4-time improvement in inference energy. I will admit that this comes at the cost of performance. You have to really slow down a little bit to make sure that just random jitter noise in your system doesn't kill your inference. And when you slow down, you're from 4 to 5 times slower than the standard digital implementation. However, this is again still much faster than a spiking neural network architecture that achieves the same accuracy. So that comes to the end of my work, but we showed that these artificial neural network operations have a clear temporal analog that can be efficiently approximated in CMOS. And in the paper, we really spent a lot of time showing how the architectural design can really change the accuracy and energy performance of these systems. Thank you.